Continuing along the lines of our discussion of estimating areas under curves, we're going to introduce a new notation for summations. And with that summation notation, we'll express areas under curves in a general form. And then we'll take limits of those sums, and that'll produce the precise areas under the curve. So the notation we'll use is called a sigma notation, the section sigma notation and limits of finite sums. We'll still do some initial approximations of areas in this section, but we'll actually take some limits and find exact areas under a curve, something formally to be defined in the next section. The summation notation we use is called sigma notation because the Greek letter capital sigma is used. Sigma sort of corresponds to our letter S, S for summation. And when we write something of the form sigma k equals 1 to n a sub k, what that represents is plugging in k equals 1, getting out a sub 1, and then adding, plugging in k equals 2, getting a sub 2, and then adding, and keep iterating that parameter k up to its upper bound of n. So this is simply shorthand notation for a sub 1 plus a sub 2 plus a sub 3, dot, 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 plus a sub n. So it must be that the a sub k is some kind of function of k in its most general form. For us, those functions will be fairly elementary, but that's what we're getting out of this summation notation. The parameter k is called the index of summation. The lower bound down here indicates where the sum begins. The upper bound indicates where the sum ends. Our sums will almost always start at k equals 1 and will most often end at k equals n. Not exclusively, but mostly we're interested in just a small special collection of these summations. We'll illustrate it in a more general sense though. A sub k is some function of k. For us, those functions will be fairly elementary. And a sub k is called the kth term of the sum. So the book gives a little diagram of the summation notation labeling all the parts. Possibly you've seen this type of notation before with some exposure to statistics where you calculate arithmetic means or standard deviations and variances and such. Let's look at a couple of examples illustrating the notation. Okay, first, let's simply take the sum from k equals 1 to 3 of k minus 1 divided by k. Write the sum without the sigmas and evaluate the sum. So we've got a lower bound of the index k of 1 and upper bound of 3. So we'll have terms for k equals 1, 2, and 3. A sub k is this function here, this formula in terms of k. So the sum from k equals 1 to 3 of k minus 1 over k is, simply put parentheses where we've substituted in the values for k. K is here, substitutions here. K equals 1, k equals 2, k equals 3. Produces, this is 0, this is 1/2, and this is 2/3. 0 plus 1/2 plus 2/3. Crunch the numbers, get the common denominator, and that simplifies to 7/6. So this sum from 1 to 3 corresponds to summing these three particular numbers here, which result from plugging k into the formula. Let's do it in the other direction. Express the sum 1 plus 4 plus 6, 1 plus 4 plus 9 plus 16 in sigma notation. Okay, well, we need a formula or function that produces 1, 4, 9, and 6 using consecutive integers. Well, 1, 4, 9, and 6, that's the squares of the natural numbers 1, 2, 3, and 4 in order. So we could take 1 plus 4 plus 9 plus 16 and write it as 1 squared plus 2 squared plus 3 squared plus 4 squared. Or a sum from k equals 1 to 4 of k squared. We got the function. I plug in k equals 1, I get 1 squared. I plug in k equals 2, I get 2 squared, 3 squared, and 4 squared, ending at an upper bound of 4. Next, we've got some properties, algebra for finite sums, as the text calls it. These are totally unsurprising results because you're so familiar with manipulating finite sums, distributions and associativity and commutativity, or properties of the real numbers you probably don't even think about. There's proofs of these given in the appendix A2 on mathematical induction. They're included in the video on that section. They're included in the notes on that section as well. So proofs of these things are available for you, but let's not right now worry about that. The sum rule says the sum from k equals 1 to n of a sub k plus b sub k equals the sum of the a sub k's plus the sum of the b sub k's. Of course it does. That rigorously really just follows by commutativity of addition. So you can add the a's together first and then the b sub k's, or you can sum them together. Differences will behave in the same way. The sum of a sub k minus b sub k is the sum of the a sub k's minus the sum of the b sub k's, again, ultimately based on commutativity. The constant multiple rule, sum from k equals 1 to n of a constant c times a sub k, you can factor that c out. Of course you can. That's distribution of multiplication over addition, really. The constant value rule says the sum from k equals 1 to n of c. Remember that would represent c plus c plus c plus c plus c plus c n times. So that's n times c. Proofs are given in that appendix. These seem like maybe almost a silly thing to bother with, but we're going to base integration in the next section or two on these kind of sums. When you see properties of sums, there's probably a corresponding property for those integrals. So just as we looked at some properties of limits and saw those properties of limits had corresponding properties for derivatives, because derivatives were limits of certain kinds of things. Well, integrals are based on finite sums. They're not finite sums, they're limits of finite sums. And when we look at properties of integrals, there will be properties of integrals that exactly correspond to these properties of summation. So again, not that you're surprised by any of this stuff, but we're building up a body of knowledge here. And you'll see these ideas reflected again when we formally define integrals and we go through and look at properties of integrals. Let's illustrate the use of these properties in some summations. Exercise 18, parts A, B, C, and D at least, says suppose the sum from k equals 1 to n of a sub k equals 0. Suppose the sum from k equals 1 to n of b sub k equals 1. I don't know what the a sub k's are. I don't know what the b sub k's are, but when you add them up, that's the information they've given us. They ask you to find several things. The first one being the sum from k equals 1 to n of 8 times ak. All right. Well, that theorem we just saw, part 3, the constant multiple rule, says you could bring constants outside the summation, really just distribution. So let's bring the 8 outside the summation, justification being theorem 5.2, point A, part 3. And you know what the sum from k equals 1 to n of a sub k is because I told you that. It equals 0. So we'll replace the sum with its value of 0, and the given quantity must have a value of 0 as well. Part B, same thing, except it uses the b sub k's. Suppose we had a sum from k equals 1 to n of 250 times b sub k. Well, I can bring the 250 out. I can factor it out. Strictly speaking, I'm using theorem 5.2, point A, part 3 again, the constant multiple rule. Do you know what the b sub k sum to? Yeah, they told you that as well. Sums to 1, so we've got 250 times. The value of this stuff here is 1, 250. So pretty straightforward stuff. Part C, as you consider a sum from k equals 1 to n of a sub k plus 1. Okay, now this plus 1 is inside the summation, so be careful with the notation. This one's a tiny bit more involved. Well, the sum of a sum is the sum of the sums. So it's almost as if we were distributing the sigma symbol. It's not distribution, it's the sum rule that we're using from theorem 5.2.a. So we can break this up into two sums. Now we've got a sum of the a sub k's first. Want to know what that is? They told us that was 0. And we got a sum of 1 n times. That's 1 plus 1 plus 1 plus 1 n times. Well, that's just n times 1, which makes perfect sense. We did have a rule called the constant value rule. It was part 4 of that theorem that establishes that. So we've got 0 plus n, and n is the value of this particular sum. Part D, similar thing, they're subtracting, and the behavior will be similar. Sum from k equals 1 to b sub k minus 1 in part B. Express that, if you like, as a sum rule. And I got some couple of different ways to deal with this -1. We'll express it in terms of the sum rule. Say, the sum of the b sub k's, they told us that's 1, so the value of that is 1. The sum from 1 to n of this constant is n times that constant. The constant's -1 here. So the value we get out of this is -n, and the value of the sum is 1 minus n. So there's some illustrations of how we can break things up over sums and additions, over additions and subtractions, I guess, and how we can deal with constant multiples. It's kind of a linearity type behavior in the sense that you'll use the term in linear algebra. But there's some properties of finite sums. I expect to see integrals, which are not finite sums. They're limits of finite sums, but I expect integrals to have some kind of similar behavior when we get those defined. Here's 3 formulas that we will make in this section and the next section, a fair amount of use of. And these involve summing powers of the first n natural numbers. And we saw an example of this a second ago when we added 1 squared plus 2 squared plus 3 squared plus 4 squared. Well, if you were to continue that process up through n, it turns out there's a formula that gives the sum of the first n natural numbers, the squares of the first n natural numbers, the cubes of the first n natural numbers. I'm sure there's other formulas, but that's the only 3 we're going to apply. And each of these formulas can be established by math induction. These formulas not entirely obvious. And that stuff we had above wasn't very surprising. It's not clear that these claims are true, but see Appendix A.2, Math Induction. One of the main reasons for doing math induction in here is to establish these 3 formulas. Proofs are given as indicated here in the notes in that appendix. There's a video and there's notes online. Why we need these, we'll show shortly. Okay, the first n natural numbers. Suppose we take the sum from k equals 1 to n of 1 plus 2 plus 3 plus 4 up through n. The claim is you'll get for that sum n times n plus 1 over 2. For example, if I added up 1 plus 2 plus 3 up through 100, we get 100 times 101 divided by 2, which was like 5,050, I think. Done. I mean, that's quicker than doing the actual arithmetic. There's a formula that expresses the sum of 1 plus 2 plus 3 up through n. Say, if we had the squares of the integers. So now we're adding 1 squared plus 2 squared plus 3 squared plus 4 squared and so forth up through n squared. In terms of n, here's what that summation is alleged to be, justified in the appendix. If we were to add together the cubes, 1 cubed plus 2 cubed plus 3 cubed and so forth up through n cubed, then you get this formula. Sure, it's not entirely a coincidence, but this formula is the square of the first one. So anyhow, there's the formulas that give such sums. Let's illustrate them first, and then we'll see why we're particularly interested in these particular summations. Let's look at 24 and 28 in the supplements. Okay, here it says evaluate the sum using those formulas, using theorem 5.2.b. Sum from k equals 1 to 6 of k squared minus 5. Okay. The sum of, a little difference here, can be written as the difference of the sums of the constituent parts. That's the difference rule from theorem 5.2.a. And here we've got a sum from k equals 1 to 6 of k squared. Well, there's a formula for that. It'll be a formula involving the parameter 6. We had the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. That's the theorem 5.2.b stuff. So we'll simply plug 6 into this formula, and that's the sum of the first part. So 6 times 6 plus 1 times 2 times 6 plus 1. So substituting the 6 in, the parentheses indicate the 6's that have been substituted in. That was part of the formula, that 6 in the denominator, as is the plus 1's. So I put in parentheses the things that are substituted. So there's the sum from, what's the sum of what? 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Not that I couldn't do it by hand. We're going to have some settings where I need these formulas. And doing it by hand, quote unquote, is not an option. So anyhow, using the formula just to illustrate its use, we get this quantity here. We'll simplify it in a second. Here we've got the constant 5 added to itself 6 times. We'll get 6 times 5. That was called the constant multiple rule in theorem 5.2.a, by the way, to give a reference. But we've got this number minus that number. And let's see, this is 6 times 7 times 13. 6 times 7 times 13 over 6. 6 times 5 is 30. We'll subtract 30. And when all the dust settles on the arithmetic, I guess we get 61. So there's an illustration of the use of the summation formulas for the squares of the first 6 natural numbers. Evaluate this sum. Okay, they're summing from 1 to 7. K, and they're summing from 1 to 7, k cubed over 4. What's that equal? Well, first, how about we bring this 1/4 out of that second summation. Bring the 1/4 out. It's a constant multiple. Constant multiple rule for this setting says you can bring constants out. Continuing, so here's the same thing we had on the previous slide. We brought the 1/4 out. You got a formula for this, and you got a formula for that. So the plan was to get the powers of k by themselves in these formulas, because that's the thing you know how to evaluate. Sum from 1 to 7 of k, that would be sum from 1 to n of k is n times n plus 1 over 2, so we'll have 7 times 7 plus 1 over 2, parentheses indicating where I've replaced the n's. For the cubing, we had the formula sum of the cubes, 1 to n is n times n plus 1 over 2, and all of that gets squared. So we'll have 7 times 7 plus 1 over 2, and all of that gets squared. So using the summation formulas and evaluating those, it's just a matter now of crunching the numbers. 7 times 8 over 2, it's 7 times 4 is 28. Oh, here we've got 7, we got 28 again, same quantity, but it gets squared and divided by 4. It must give 196. When the dust settles, we get negative 168, it looks like. But there's an illustration of using the summation formulas for the powers of k again. Now, it looks like we're shifting gears here. We'll be back after those particular summation formulas here shortly. In the last section, we drew rectangles under functions and made estimates of the area under those functions. We made some claims about the values of certain areas as well. We're about to establish one of those area claims. So with an eye towards area under functions, that's the reason we're doing this, a partition of the interval from A to B is a set of the form x sub 0, x1 through x sub n, where a equals x sub 0, the first indexed x value, b equals the last one, the x sub n, and they come in the order that's indicated, x0 less than x1 less than up through x sub n. So they're all different for one thing. So we've taken, a good little picture is given here, we've taken the interval, here's the real line, from A to B, and we've cut it into some pieces. We've cut it at x sub 1, we've cut it at x sub 2, blah, blah, blah. We cut it here, x sub n minus 1 to x sub n, with the following rules. These may not be evenly spaced. They come in the order given, but nobody said they're evenly spaced. We'll often consider examples where they're evenly spaced because arithmetic is manageable in those cases, but that's not going to be part of the big picture. Partition P then determines in closed subintervals the interval between x0 and x1. Closing it off, the interval from x1 to x2, the interval from x2 to x3. The subintervals are these little intervals here, x0 to x1, x1 to x2. Here's what we'll call the kth subinterval. It'll be the one that has left endpoint x sub k minus 1 and right hand endpoint x sub k. Notice the first one has an x sub 1 as its right hand endpoint. The second subinterval has x sub 2 as its right hand endpoint. So the kth subinterval has x sub k as its right hand endpoint. And the last one, this would be the nth one, has x sub n as its right hand endpoint. The length of the kth subinterval we're denoting is delta x sub k. So it'd simply be the right hand endpoint minus the left hand endpoint. X sub k minus x sub k minus 1 for the kth one. And that's valid for any k between 1 and n. So we get the picture in terms of the lengths is something like this. Delta x1, length of the first subinterval. Delta x2, length of the second interval. And it looks like in this picture, the second one is longer than the first one. Looks like delta x sub k is the largest of those that are labeled here, probably simply because of typesetting reasons and more than anything. But we partition the interval from A to B into pieces. That's determined subintervals, and we're interested in the lengths of those subintervals. We were doing stuff like this in the previous section. In the previous section, those numbers in the partition were evenly spaced. And in this section, when we do computations, we'll probably take them to be evenly spaced as well. But nobody says these x0, x1 through x sub n, the points in the partition, nobody says those are evenly spaced necessarily. Computationally, we'll take them to be evenly spaced. All right, the following picture is the most important picture in Chapter 5. Giving an idea of where we're going with this area estimation and ultimately with this idea of an integral. We now estimate the area bounded between a function y equals f of x and the x-axis. Okay, we make the following convention that the area bounded above the x-axis and below the function is positive, and the area bounded below the x-axis and above the curve is negative. Well, areas aren't negative, but in this technique we're introducing, it's going to treat places where the function is negative as producing areas which are negative, which means if you want straight up areas, you better be careful because you're getting these areas to count as negative. So here's what that means in terms of a picture. We'll come back and read the rest of that. Here's a curve, y equals f of x, and we're going to partition the interval from A to B up. A is here, B is here. So we've partitioned it up. It's got some little pieces and some thicker, fatter pieces. And we're going to use function values to determine heights of rectangles. So as in the previous section, it's a story about base times height. We're going to use function values for the height. No problem. On the right, where the function's positive, you choose some number c sub k, as we did in the previous section, between x sub k minus 1 and x sub k. The stuff we've illustrated so far has involved left endpoints, right endpoints, and midpoints, as we'll often do, especially when computing things. But that's not part of the big picture either. C sub k could be anything in this little subinterval. Well, that's going to produce a function value that's positive. Can you find the area of this rectangle? Sure. It's that distance, which we call delta x sub k, times this function value, f of c sub k. The function value is positive. The delta x sub k's were always positive. They were lengths of intervals. But the function values ain't always positive. They are over here on the right. So when I take width times function value, I get a positive thing out. It's the area of this rectangle. When I take width times function value, looks like we're using this one right here, possibly this one right here. We're using a function value. It's positive, represents the area of this rectangle. Positive area, positive area. But over here in the first and the second and the third and the fourth rectangles, we've used this c value, c sub 1, and we've plugged it into the function. Now, if I take the width of this interval and multiply it by this function value, and that's what we're going to do, function value is negative. We don't get the area of this rectangle. We get the negative of the area of this rectangle. Yeah, it's because you're computing heights, quote unquote, using function values. If they're positive, they are heights. I mean, height means distance. Distance means not negative. But over here on the left, if we're using function values for heights, sometimes we're getting negatives out. On the left-hand side, we're getting negative function values out. So we're getting negative heights. All right, give me a little verbal break. And let me call them heights or quote unquote heights. Okay, technically they're not heights because they're negative, and heights are distances and distances aren't negative. But the thing we're going to set up is going to treat these as if they were negative areas. That's the convention I'm getting at. So what we're going to do is take widths times function values. Well, that's going to produce some negative areas, quote unquote areas. So I'll do the quote unquote thing for a while, and then I will get tired of that. But be careful, when the function is negative, this procedure is treating these as if they were negative areas. And when we add all this stuff up, this part is contributing positive areas. This part is contributing negative areas, quote unquote. That's the technique we're dealing with. That's the kind of numbers it's going to produce. So I say let's treat it as a convention. It's really more an artifact of the way we're going to define the upcoming ideas. So we estimate this quote unquote area by choosing a c sub k in the kth subinterval, and we use the function value as the quote unquote height. The rectangle that results, quote unquote rectangle, arguably, has the base x sub k minus 1 to x sub k. So we found a width and a quote unquote height. With a partitioning, that allows us to estimate the quote unquote area by adding up the quote unquote area of the resulting rectangles. So the procedure we're going to use would produce this area plus this area plus this area plus this area minus the area of this rectangle minus the area of this rectangle minus this one minus this one. Or it would produce the quote unquote area of this one, but it's negative, plus this one, plus this one, plus this one, but all four of those are negative, plus the areas of these. So if you'll let me call area negative or quote unquote area negative, it produces, I don't know, the area here minus the area there. The function being negative is causing a problem with an area interpretation. All right, well, just be careful about that. It'll be fine. In the previous section, if you dissect what they did, they never dealt with functions that were negative. They always dealt with non-negative functions in the examples in the previous section. I think I had maybe mentioned quote unquote areas along the way in the conversation, but none of the examples had functions that went negative in section 5.1. Okay. With the notation established above in terms of function values and partitions and delta x sub k's, we define the Riemann sum of f, or a Riemann sum of f on the interval from a to b to be a sum of this form. S sub n, that's for sum, n because we're taking a partition that results in n subintervals. Sum from k equals 1 to n, f of c sub k times delta x sub k. That is then exactly in the picture above. I'm going to see the picture and the sum at the same time. Force isn't with me too much on that. All right, so that gives us f of c sub 1, this function value, times delta x sub 1, the width of this rectangle. It's width times function value. I'm thinking area, but I got a negative that comes out because the function's negative. K equals 2, width, delta x sub 2, times the function value at c sub 2, which is negative. I'm thinking area, I'm getting negative numbers though. Similarly here and here. Over here, same thing, width times function value. It's positive over here, so I can legitimately say area over here. On the right, we've got legitimate area. On the left, we're getting negatives of areas because we're dealing with Riemann sums. Then we've got this issue about when the function is negative in an area interpretation. You want to fix all that, slap an absolute value on the function, you'll be good to go. Yeah, the technique we're going to have isn't going to like absolute values of functions too much though. And the way we're establishing this Riemann sum stuff is the way everybody establishes Riemann sums. Just be careful when you talk area. There's a problem with that when the function could be negative. No problem at all when the function's non-negative. When the function's negative, we got some issues in terms of area interpretations. So Riemann sums don't always represent actual areas. They represent quote unquote areas. The problem that arises when the function could be negative. Let's look at 5.2.38, which says, graph the function. This is just a matter of drawing pictures, is all I've asked in this one. We'll do plenty of the arithmetic here shortly. Graph the function f of x equals negative x squared over the interval 0 to 1. Okay, that function's non-positive, so it depends how much I want to talk about area. I got a lot of air quotes to throw in if I talk about areas in this one. Let's talk about Riemann sums. And then you just know that there's some concerns over area interpretation. The Riemann sum is unambiguous. Partition the interval 0, 1 into 4 subintervals of equal length. Okay, we don't have to use equal length intervals, but they've told us to. Then add to your sketch the rectangles associated with the Riemann sum from k equals 1 to 4, f of c sub k, delta x sub k, given that c sub k is the left-hand endpoint, part A, part B, the right-hand endpoint, part C, the midpoint of the kth subinterval. Okay, they didn't ask us to do the arithmetic on the summing. They asked us to find the Riemann sum. Okay, and draw pictures, basically. All right, so the pictures we get are as follows. Here's the graph of y equals negative x squared. It's a concave down parabola. I mean, you're familiar with graphing y equals x squared and y equals negative x squared. I'm only interested in what happens between 0 and 1. The area, which we're approximating, I've given in yellow. So we're interested in the area bounded by the x-axis and this function for x between 0 and 1. This is the area of interest. This is the area we're going to approximate as described. So partition the interval 0, 1 into 4 subintervals of equal length. Okay. 0 to 1, break it into subintervals of equal length. There you go. The partition is 4 subintervals. That'll mean 5 endpoints as we start at x sub 0. The partition we're using is is 0, 1/4, 1/2, 3/4, and 1. That was 5 numbers, 5 endpoints produce 4 subintervals. The subintervals are 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and 3/4 to 1. 4 subintervals, 5 endpoints. Okay, there's the partitioning, along with the rectangles based on left endpoints. Okay, so left endpoints, I'll go through, well, let's start on this rectangle here. So I want to use the left endpoint of this 4th subinterval. Left endpoint is 3/4. I'll plug 3/4 into the function. That'll produce this y value, and we'll use that as a quote-unquote height. The corresponding rectangle in the picture, as relates to the Riemann sum, this is the 4th rectangle. We use the left-hand endpoint. Here, left-hand endpoint, 1/2. Go down to the function, determines the quote-unquote height. Second subinterval, left-hand endpoint, go to the 1/4 to the function, determines the quote-unquote height. There you go. First one, use the left-hand endpoint, that's 0. Plug that into the function, you get 0 out. We've got a height 0 rectangle there, so that one's a little weird, but that's what you get. So here is the 4 rectangles. Okay, one of them maybe is a degenerate rectangle. It's height 0, but these are the, let me count it. These are the 4 rectangles associated with the Riemann sum when we use left-hand endpoints. Can you figure out what we've got for delta x sub k? Yeah, they're all 1/4. All these intervals are width 1/4. Now you broke the interval 0 to 1 into 4 pieces. Of course, the pieces, it being the same size, are 1/4. How about the function values? Yeah, I plug 0 in, we get 0 out. I plug 1/4 in, we get negative 1/4 squared out for the function value. That's the f of c sub 2. That'd be 1/4 squared, be negative 1/16. That's what we're getting out for the function value. Yeah, you're getting negative values out. Okay, well, that's what the Riemann sum is going to produce. In part B, they said, draw a picture of the same thing, except use right-hand endpoints. Okay, in the first subinterval, the right-hand endpoint's 1/4, so we'll use that, and that produces a rectangle that looks like this. The y-coordinate is negative 1/16. We were just talking about that. But in the first rectangle this time. Second rectangle, we'll use the right-hand endpoint, 1/2. We'll go down till we reach the curve and the corresponding x value of 1/2, and that determines a quote-unquote height there. Thirdly, use the right-hand endpoint 3/4, determines a height, quote-unquote. Right-hand endpoint determines a height, quote-unquote. I'm still getting the negatives out when I do the Riemann sum stuff. Yeah, we're dealing with a negative function. So there's what we get in terms of a picture when using right-hand endpoints. The arithmetic, we could crunch through the arithmetic and get the area estimated. The area of the yellow estimate by adding up the quote-unquote areas of the orange rectangles. Remember, the function is negative, so we'll get negative numbers out for those Riemann sums. Midpoints. Okay, same idea. I've got the same partition. Now I use the midpoint. I drew a little thin line at the midpoint. The midpoint here is what? 1/8. The midpoint here, I think, is 3/8, 5/8, 7/8. That's what you get for the midpoints. So I could go through and use those midpoints now to determine heights of rectangles. We saw in the previous section that midpoints gave pretty good numerical estimates of actual areas, quote unquote, in this section. So I would expect numerically this to be better than that. If you had to do the arithmetic, which do you like best? Left-hand endpoints, right-hand endpoints, or midpoints? Well, midpoints are a little more arithmetically awkward. I think the arithmetic will go more smoothly for if you use left or right-hand endpoints. more of that shortly. Numerically, you get a better estimate, I suspect, when you use midpoints, however. All right, let's see. Well, let's do one of these in all its glory. Example 5.2.5 says, partition the interval 0 to 1 into n subintervals of the same width. Give the lower sum approximation of the area under that function based on n, and, new stuff, find the limit as n approaches infinity of that lower sum. When n approaches infinity, the width of the subintervals will approach 0, and the number of subintervals will approach infinity. All right, first off, is that function non-negative? It is on this interval, so I don't have to sweat over quote-unquote areas. We're dealing with a non-negative function over the relevant interval. Okay. This is a big conceptual example about what definite integrals are, to be defined shortly. But that's where we're going with this summation stuff. Okay, so partition the interval 0, 1 into n subintervals. Okay, maybe it looks something like this. This is an image from the book. I think there's like 16. We've used this image before. I think there's like 16 things in the partition, but just interpret that picture as you've cut the interval 0 to 1 into a bunch of pieces, n pieces, each of the same width. So we're assuming evenly spaced in this example. That's not part of the big picture. That won't be part of the definition of definite integral. But when we compute one of these, it's probably going to be part of the story. And it's sufficient to do this to be established later. Here's the curve. It's non-negative. We want the area under this. We had looked at this in section 5.1, and we had claimed it was 2/3. Remember the 0.666666666 thing, and we had numerically approximated it. We're going to show it's 2/3 in this example. All right. So there's the picture, and there's the plan. I don't got to do no quote-unquote stuff with areas because this function is non-negative. So it's totally an area computation. So we need to partition the interval into n subintervals. Let's do that first. If we partition the interval 0, 1, a, b in general, to use the notation we'll commonly use, into n subintervals of the same width, then the width will be the length of the interval divided by n. This interval is length 1 divided by n. Each of the little pieces will be 1 over n. When you add all those 1 over n's up, all n of them, you get 1 out, which is the length of the given interval. More generally, if a and b are not 0 and 1, then we'd express the length of those subintervals using this formula. What are the resulting subintervals? Well, those will be, I claim, x sub k equals a plus k delta x, where delta x is this 1 over n parameter. Let's see if I can convince you of that. So we're taking, here's x sub 0, x sub 1, x sub 2, and so forth. This image isn't in the book. I made this one. It looks like the one in the book, though, by design. We're taking the same size steps from one x to the next in the partition. And we started at a. So what do you get for, say, x sub k? Well, how many steps from here did you take? You took 1 step, 2 steps, blah, 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 k minus 1 steps, k steps. You took k steps. How big were those steps? Delta x. All the same size. So x sub k must be where you started, x sub 0, or a, plus the number of steps of equal size you took to get there. X sub k is given by x sub 0 plus k times delta x. Well, x sub 0 and a are the same. If you like, it's a plus k times delta x. Here, we started at 0. So we get 0 plus k times, here, delta x is 1 over n. 0 plus k times 1 over n simplifies to k over n. That's what x sub k is. So We've got a partition. We've determined what the x sub k's are, and we're going to end up using those x sub k's in the function because they told us to. More of that in a sec. But these are general formulas when we have partitions of the same width. Here's what the delta x is, and here's what the x sub k's are here for our value of a and our interval that produces k over n. And there's an image of what's going on. All right. 1 minus x squared, that's a decreasing function. Its derivative is negative on the interval 0, 1. And you saw the picture of it on the previous slide. They told us to give a lower sum approximation. Okay, decreasing function, lower sums, we'll use the right-hand endpoint because it's a decreasing function. The function on the little subinterval will be at its lowest on the right-hand side of that subinterval because at x sub k minus 1, it has a certain value and it has a lesser value because it's a decreasing function on the subinterval at x sub k. So use right-hand endpoints because for a decreasing function, that'll give you the smallest, the lower function value on those subintervals. That is, we're going to take c sub k, the value we plug into the function, to be x sub k, the right-hand endpoint of each subinterval. In this case, it was k over n. All right, Riemann sum time. So we know the function, they gave us that. We know the partition. We know the x sub k's. We know the c sub k's. And we know the delta x sub k's. They're all the same. Let's just denote it delta x. C sub k is k over n. Delta x sub k is denoted delta x because we took them to be the same. Otherwise, we get totally lost in the arithmetic. That's 1 over n in this case. By the way, a common term for a partition in which all the little pieces are the same size is called a regular partition. I don't recall seeing that in the book, but this is common terminology. Then we have the following Riemann sum. So Riemann sum would be a sum from k equals 1 to n of f of c sub k times delta x sub k. The delta x sub k's, they're all 1 over n, so I'll substitute that in. And we've chosen c sub k to be those right-hand endpoints, k over n in this case. So substituting in the c sub k value and the delta x value produces this. What's the function? We're dealing with a function, 1 minus input squared. We'll input k over n, so we get 1 minus k over n squared, parentheses, because I've substituted. So the Riemann sum at this stage is of this form. Let's modify it. Let's see, we're summing from k equals 1 to n. So the k's change in this summation, but 1 over n's a constant. So let's bring that out front, constant multiple rule, if you like, leaving us with a 1 minus k over n squared. Let's write that as 1 minus k squared over n squared. We got the 1 over n out front, having factored. This is a sum of little differences, so we'll write it as a difference of the sums. Don't forget to distribute the 1 over n. So we'll have 1 over n times the sum from 1 to n of 1. And there's the first one. In the second one, we've got minus 1 over n sum k squared over n squared. Let's bring the n squared outside of that sum. 1 over n squared out of that sum. Combining the n squared with the n to produce an n cubed. Convince yourself of the arithmetic. I did skip a step of algebra on that. But I want to see either constants or powers of k, because those are the things I have formulas for. So taking the Riemann sum, it can be put in this form. Do you know the sum from 1 to n of 1? Yeah, it's n times 1. The constant case, or whatever they called it. It's 1 plus 1 plus 1 n times. So of course, that adds up to n. And we had a result to justify that. We got the 1 over n cubed. How about the sum from k equals 1 to n of k squared? We had a formula by theorem 5.2, point B, part 2. The sum of k squares from 1 to n is given by this. So we've got the Riemann sum written in this form. They said Subintervals give the lower sum approximation. Okay, that's this right here of the area under the curve based on n. Done. There's our lower sum approximation, or if you will, our Riemann sum, a Riemann sum approximation of the area under the curve. Next, find the limit as n approaches infinity. Okay, so here's the Riemann sum. From the previous page, let's simplify a little bit, cancel the ends, leaves us with a 1. I can cancel that in with one of these, leaves us with an n squared in the denominator. So let's simplify it a little bit and take a limit as n approaches infinity. Limit as n approaches infinity of this Riemann sum is a limit as n approaches infinity of this quantity above. You know properties of limits. As the variable approaches infinity, limit of the difference is the difference of the limits. The first one's a constant, so we get a 1 out. Notice our somewhat more cavalier attitude toward limits here in chapter 5, because we got other stuff on our minds. Limit as n approaches infinity of the quotient part. How do you deal with that? How about we multiply the numerator out? That'll give us 2n squared plus 3n plus 1. Foil it. Never get too old to foil. We'll divide numerator and denominator by the highest power of n this time. Usually we had x in the past, but n this time. In the denominator, highest power of n in the denominator is n squared. So we'll divide numerator and denominator by n squared by multiplying by the appropriate thing. Distributing the n squared. So here it's written in the quotient. Distributing the n squared, we'll have 2n squared over n squared, producing a 2. 3n over n squared, producing a 3 over n. 1 over n squared, 1 over n squared. 6n squared over n squared. Cancel the n's. So doing these limits a little bit faster than we did in the past. Take a limit of this stuff. Limit of the quotient is a quotient of the limits. Unless the denominator is 0, and it ain't, it's 6 in this case. And then the limit of the sum is the sum of the limits, constant multiple rules. Get that limit on the 1 over n's. Here's a 1 over n with a 3 out front. Here's a 1 over n, but it's squared. Okay, here's a limit of n approaches infinity, 1 over n, and it's squared. You don't know much about limits as things go to infinity, but you know that's 0, and we've always dealt with these in that sense. I guess you could argue L'Hopital's rule could be used as well. This is an infinity over infinity indeterminate form that we've got at this stage. But here it is written up in terms of the 1 over n idea. We get 0 here, I get 0 squared here. So evaluating those limits, simplify, and we get 2/3. I told you it was 2/3. There's why it's 2/3. So we've got a precise value for the area under that curve based on adding up finite things and then taking that finite stuff and making it better and better by making n larger and larger. What you've accomplished by making n larger and larger is you're cutting the area into smaller and smaller pieces uniformly, because we took all the pieces to be the same size. That idea is what we'll have for the definition of a definite integral in the next section. A little more terminology. The norm of a partition P, x of 0 through x of n, of an interval a, b, denoted with these sort of double absolute value looking things. It's called a norm. This is a fairly common term. There's other terms for it. We need this in the next section. But the norm of the partition is the length of the largest subinterval. It's the maximum delta x sub k. There's how we calculated the delta x sub k's. We just did an example where the delta x sub k's were all the same. But remember, they don't have to be. The norm of a partition is the length of the biggest piece. We've been approximating things, approximating and taking limits in this section. But here's that same graph, that same function we had on a couple of slides ago, where I was going on about negative over here and positive over here. We had a picture back there where we cut it into, I don't know, 7 or 8 pieces. Just because you cut it into a lot of pieces doesn't mean you're getting a good approximation. What you need to do is cut these regions into small pieces. Now, I could have big chunks over here and have an infinitely many number of little pieces over here. Well, I'll have an excellent estimate over here, but not so good necessarily over there. It's not in general about having lots of pieces. It's about having small pieces. If I got lots of pieces and all the pieces are the same size, then they will be small. But the big idea is to have small pieces, not lots of pieces. We do get lots of pieces, we do get small pieces when we have lots of pieces, and we use practicing my vocabulary here, regular partition. If it's a regular partition, all the pieces are the same size, and lots of pieces mean you must have small pieces, and it's small pieces that matter. In other words, if the norm of the partition is small, well, the norm of the partition is the largest subinterval. Well, if the largest one's small, then they all small. So that's the big idea behind looking at the norm of a partition. It's kind of the worst subinterval. It's the widest one, the one of greatest length. And I want narrow subintervals. Well, if the biggest one's narrow, then they all narrow is the idea here. So we get good approximations when the norm of a partition is small. Cut it into small pieces and you get better approximations of the area. If AB is partitioned into n subintervals of equal length, that length is b minus a over n. In this case, when n goes to infinity, the norm of the partition goes to infinity. This is the norm of the partition. N gets large, this gets small. So as I just said, by having n approach infinity in a regular partition, all subintervals are the same length, then we get the norm forced to go to 0. And that's a good thing. That's how we'll define integrals in the next section, I think it is. One last example, actually quite similar to the one we just did. Consider the function f of x equals 3x plus 2x squared. Find a formula for the Riemann sum obtained by dividing the interval AB 0, 1 into n equal subintervals using the right-hand endpoint for each c sub k. Then take a limit of these sums as n approaches infinity to calculate the exact area under the curve over this interval. First off, is that a non-negative function on the interval 0, 1? Yeah. So I don't have to go through a bunch of quote unquote stuff with areas. We could apply this same technique to functions which are negative. And then technique's the same. Interpretation has to be tweaked a little bit if I want to talk about areas. Okay, as before, in the previous example, take the interval 0, 1, cut it into n subintervals of the same width. Use a normal partition. That width will be delta x equals 1 over n as before. The subintervals will be, as before, their width will be, so I dealt with the width is 1 over n. The endpoints will be x sub k equals the starting point a plus k times delta x, as in the picture we had above. Again, it'll be k over n. So we've got the same interval in the same kind of partition. So we get the same kind of x sub k's, and we get the same kind of delta x's as we had in the previous example. What changes is the function. We're using the right-hand endpoint for c sub k because they told us to, and we did that in the previous one as well. We did that in the previous one because they told us to use a lower sum. Here, they're just explicitly saying, use the right-hand endpoint. Is this a lower sum? Can you tell? We could figure it out. Is this a decreasing function or an increasing function or what? We could figure it out. We got plenty of equipment to determine whether this is an increasing or decreasing function on this interval. Doesn't matter. They told us to use the right-hand endpoint. As they often will, it simplifies arithmetic. Use the right-hand endpoint. Okay, right-hand endpoint of the k subinterval is x sub k, just like last time. So c sub k equals k over n again. So like last time, in the previous example, the Riemann sum is as given here. sum from 1 to n of f of c sub k, delta x sub k. All the delta x sub k's are 1 over n. The c sub k's we've chosen to be k over n, and we sum from 1 to n. This is the exact same thing we had in the previous example. What's different here is the function. The function f is now 3x plus 2x squared. So we'll plug k over n into that function and get 3 k over n plus 2 k over n squared. 3x plus 2x squared, evaluated at k over n, produces this. What's going to happen next? Well, I'm going to multiply this stuff out, and I'm going to try to isolate those powers of k. We'll have a k to the 1, we'll have a k squared. We'll get those by themselves in summations, and we got formulas for the sum from 1 to n of k and k squared. I've got some n squareds and some 2's and 3's in the conversation, but we'll treat those with appropriate mathematical respect. Here's where we left off on the previous slide. So let's bring the 1 over n out front, constant multiple rule. Let's clean this up a little bit. Write it as 3 over n times k. Write this as 2 over n squared times k squared. And I got my eyes on the powers of k. Those are the things I want to get to in the summations because we've got formulas for those. Let's break this into a sum of 2 summations. In the first, we'll factor the 3 over n out, giving us 3 over n squared. In the second, we'll factor a 2 over n squared out. The 1 over n gets distributed still, giving us a 2 over n cubed. Pause and convince yourself of the arithmetic if that's a problem. But we've isolated the sum of the k's and the sum of the k squares. And we know what those are. We've got a formula for this. We got a formula for that. Sum from 1 to n of k is this formula here. Sum from 1 to n of k squared is this formula here. That's theorem 5.2, point B, parts 1 and 2. Part 3 gave the sum for cubes if that was an issue. But we've got formulas for those. So substitute in, simplify if you can. I can cancel this n, one of these n's with that n, leaving us with a 2n in the denominator. N in the numerator is gone. Here I can cancel the 2 and the 6 to give us a 3 in the denominator. I've got an n cubed and an n. I can cancel one of those to get an n squared in the denominator. There's the Riemann sum in terms of n when using a regular partition for this function on the interval 0, 1. All right, so there's the Riemann sum. Now it's a matter of taking a limit as n approaches infinity. Take a limit as n approaches infinity of the Riemann sum. That's this quantity here. Let's go through this a little more quickly than usual. You've got the notes and you can pause the video, but it's the same technique we had before. I'll multiply out here. That'll produce, where have I multiplied out? That'll produce a product, something of this form. We've got power of n in the denominator in this first limit, so we'll multiply by 1 over n over 1 over n. Here we've got an n squared in the denominator. We'll multiply by 1 over n squared, 1 over n squared. We'll distribute, we'll simplify, and it produces these two limits. You know the limit as n approaches infinity of 1 over n goes to 0. Evaluating that limit, everything else in that is a constant. Here we've got 3 times 1 over n, and we'll get 3 times 0 in the limit. Here we've got 1 over n squared. Think of it as 1 over n quantity squared. The limit will go to 0, well, 0 squared. So skipping some steps, since we've done a fair amount of this at this stage, but skipping the quotient rule for limits and the summation rule and the constant multiple rules, we'll get zeros for those 1 over n limits. And that produces, what do we got here? 3 halves and 2/3. 3 halves plus 2/3, I guess, is 13 over 6, 13 sixths. And that's the exact value of the area under that curve. I can say area because it was a non-negative function. And I guess that completes this section. So the big ideas were limits of Riemann sums good things when the norm of the partition is little. Maybe we'll take a limit as the norm of the partition goes to 0. We will. I think that's the next section. This is the big picture from this section in terms of area interpretations. You got to be careful treating this limit of a Riemann sum stuff as an area. It just got to be careful. It could be a negative. And when functions are negative part of the time, that has an effect on area interpretations. Just be careful with that for now, and you're good to go. Non-negative functions, none of this is part of the conversation. I can say areas outright. But we will evaluate limits of Riemann sums, and so that's the kind of sums that of which we were taking limits. We'll take limits of Riemann sums, and they have a geometric interpretation related to signed area or quote unquote areas. So we'll take this idea and run with it in the next section and formally define the definite integral of a function. And we'll evaluate a few more in terms of this limit process. I'll see you in section 5.3. Bye-bye.